Back on a problem together. The problem is sudoku-solver, and the problem statement states that write a program to solve a Sudoku puzzle by filling in the empty cells. A Sudoku solution must satisfy all of the following rules. Each of the digits 1 through 9 must occur exactly once in each row, exactly once in each column, and exactly once in each 3 by 3 sub-boxes of the grid. And there's a note that the board contains only digits 1 through 9 and the character dot, and you may assume that the given Sudoku puzzle will have a unique solution, and that the board size is always 9 by 9. Now this notes, that's some good news. First of all, that it has a unique solution. That's fantastic news, because that tells us that we are definitely going to have a solution, and that we are not going to have a curveball where we're going to be trying to solve something that doesn't have a solution, which would exponentially make this much harder. And that the both sides is 9 by 9. That makes or limits the difficulty, or bounds the difficulty of this a little bit into the realm of possible. Um, so this is good news. Now this can be solved using backtracking, recursion with backtracking. Now the idea would be to start from the cell 00 on the top left and move across each row. Look for empty cells like this one here. Test for possible values 1 through 9 which do not cause a conflict, and then try for each possible cells until we reach cell 99. We know we are done when we reach cell 88, because we're zero indexed. We know we are done when we reach this cell here. So without further ado, I'm going to start coding, and I'm going to begin with the conflict checking. I'm going to call the function move. It's going to be a boolean. It's going to check the move. The move is going to be a valid one. Or actually, that doesn't sound correct, because it doesn't give a good it doesn't give good meaning to what we're doing. So valid sounds much better. So that gives more meaning to what we're doing. Is this a valid move or not? So what this is going to take in a board. It's going to take in x coordinate, y coordinate, and it's going to take in what I'd like to call a candidate, or in other words, it's going to take in what we're going to be testing, or the value which we're going to be trying to see whether it is a valid value or not. So let's begin. Let's begin by checking the rules. Oops. Now keeping our row constant, moving our columns, I'm going to check if our candidate is valid within that row. If there's a conflict, we'll return false. Now we're going to do a similar check for our columns. Keeping our column constant. So check the 3x3 grid. Now this is a little bit complicated. Now this little algorithm is going to help us stay within the bounds of our grid. An example would be this grid here. This would be 0, 1, 2, 3, 4. No, 0, 1, 2, 3, 4. 4. So this is grid 0, 4. 0, 4, y is 4. 4 minus 1. This is modulus 1. This is 4 minus 1. That's 3. That puts us at 0, 3, which is this grid here. So that puts us exactly where you want to be at the beginning of this grid here at grid 0, 3. Then we start iterating this way. So for int r equals to row, r is less than row plus 3 r plus plus. C is equals to col. C is less than column plus 3 C plus plus. C plus plus. That's funny. Okay. So if code R C is equals to the candidate, return false. Now, if all else, return true. That should cover all the bases. Now, for a recursive call, I'm going to call it solve because that's exactly what it does. It's going to take in a board. It's going to take in excuse me if from time to time if my syntaxes are going haywire, it's because I'm used to Python. So if I forget to include some syntaxes, it's because I'm used to Python, or my mind is just in Python. So forgive me if I do that. And let's call our recursive function by passing in the board and our beginning row and column. So we beginning on the top left. Now what we said was we are starting from 0, 0, moving along the rows. So to do that, y now, to make sure we're staying within the bounds of our row, y is just going to be simply that. Now to move to the next row, it's going to be simply that. That should do it. Now check whether we are done. So we know we are done when we get to our end, which is 8, 8. But the caveat is that that we need to fill in box 8, 8 to know that we are done. So we need to check on the next iteration whether we are done. Not on, so on when x equals 9, check whether we are done. Now to avoid getting out of bounds, we check exactly after our last check, which is 8, 8. Our next check will be 9, 0. So that's exactly when we are done. Okay, now we're going to check for empty spaces, cells. So if bold x y equals to, or rather doesn't equal. Now we know that if it doesn't equal a dot, then it's a number. If it's a number, we don't want to do anything, we just want to skip recursively to the next cell and return that. Now here comes the meat of our recursive call. So we begin with our for loop. Now within the for loop, what we want to have is a list of all our possible candidates from 1 to 9. Of values that we can place within each cell, open cell. So we'd want to check if it's a valid cell, passing the board to that cell, which is cell X, Y, passing the value. Now this is a char board and this integers, so we need to add 48 to that. Now since if that is valid, time to write down the value on our board. Time to mark down the value on our board. Candidate. Same thing, add 48 to the value. Now time passing the board. Now what you're doing is going to the next cell. Is that call goes through, return true. If not, oh, actually, nope. else we backtrack, set revert our board, and return false while doing that. And we should be done. Let me look at this quickly. That looks okay. 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 We need to pass in a board to our solve. Valid, passed in our board. Okay, let's try our solution. Oops. That's an oversight. Return true. Thank you, compiler. And it looks like we got a result. Let's compare our result here. Okay, that looks similar to what we expect to find. And in fact, it's a correct result. Okay, let's submit this. Looks like we got what you were looking for. And let's see if our solution will be accepted. Okay. And it says here that our solution was runtime 12 milliseconds, ran faster than 70% of other submissions, and the memory was not half as bad. So there we go. I hope you enjoyed watching the video, and hopefully you learned something from watching the video. And yeah, I'll catch you next time on the next video. Thank you.